build upon with a decision of some kind, with a very easy decision. It can be hard to think. Sorry, man.
We multiply the n minus 1 matrices in an optimal way, I guess.
Yeah, well, what we might have is, if you think about these, what we might actually end off with are a bunch of products, right? So given the last step, we might have, like this is all going to be a product of some kind. And really what we want to do is, when you step back, and forget about the last one because it's super redundant, we might be looking at the problem of placing one bracket. When we think about placing one bracket and this, how hard is that? Right? Not too hard. Turns out that you like to consider, n combinations. You just have to figure out, stepping through your set, should I put it here? No, how about here? Well, these ones are redundant. We won't do those. You'll do, this one. No? Okay, how about this one? How about this one? And it's going to be, you only have n minus 1 to consider. Right? And so this is our substructure. So you're like, oh, this is really cool. We have optimal substructure. And it has a lot of letters in optimal substructure. On the chalkboard, gotta write them off if you're lecturing. So you have optimal substructure. What's the next step? You just said it.
Find the overlap.
Yeah, so the second step is, because if you need to have optimal substructure, the first thing you might think is, well, just divide and conquer, like some way to formulate the solution as a sum of subproblems, and it can be pretty direct to do so. But in this case, I think you can, especially given the fact that it's matrices and we're considering lots of combinations, I hope that it's somewhat clear that recursively recalculating matrix products might cost a lot. We might end up doing A5 and A6, tens, hundreds, depending on the size of the set, we might do that specific product many times. So that we do, it's very clear that we have overlapping subproblems. So we have this. So we've done 1 and 2. We've looked at the problem. We did some initial analysis. 1 and 2. So we can go straight away and start considering a recursive formulation. A formulation where maybe we consider the problem of placing one bracket in an optimal way given a subset of problems that are handed up from the previous level, and how to place that bracket in a way that is optimal, and what that problem looks like. And if we can do that problem in an efficient way, then we can formulate it in terms of one of the subproblems, and we can go from there. And we don't have to be super precise at the beginning. I mean, the idea is to try to problem solve. And I think the matrix chain multiplication problem is kind of fun because it is really a good example for how the problem solving sort of works. Yeah, so consider one bracket. Or I should say, when I say one bracket, what I really mean is a split. Where do we want to split this set into two subproducts? That's optimal, knowing that we'll be able to subdivide later. So if we consider some, let's start using our sort of set subscript notation to talk about our matrix list. So instead of R, so we use A, some I, from I to J. And yeah, this might equal AI plus 1. We're gonna run into at some point, we'll run into a k minus 1, or a k, depending on the notation you want to use, at which point that's going to be our bracket split, where we're going to consider the product of this multiplication, and then afterwards we'll continue from ak all the way to aj. So the split occurs, let's say split at k. Is there anything we have to consider with k? Straight away? Right out the gate, right off the bat? First no? K has to be obviously between I and j. So let's just get that out of the way. But because of the way the notation is, because we're using k minus 1, it can go all the way up to j. The k, yeah, it'll. Now, if you decided that instead you're going to do k plus 1, you'd have to reverse this. So just be careful with off by 1 errors and stuff. Although I don't think that anyone's going to have the patience to see your off by 1 errors. They're really annoying to notice. Can anyone think of a simple way to express the minimum cost for one split? It doesn't have to be super precise. But what do we want to do? If you think about, you're going to place two brackets, or you're going to split this set such that you want to minimize some total. How do we want to think about it? And this is where sort of loose analytics can be your friend, because it can help you. I do this a lot, especially when I'm brainstorming for clients. I'll set up some sort of loose analytics to start thinking about a problem. And then I'll make them more precise as I work my way to the solution. So let's describe the minimum cost. And the minimum cost is just going to be, for one bracket, is going to be the min, given of the theta, so the runtime of the operation where you multiply, given these guys, I to k minus 1 times a of k to j. So that's kind of like the basic idea. That's just what we want to do. But given the starting point, we can go far places with that, it turns out. Does this make sense, everybody?
So what's the notation at the end? Is I is
It's kj. So we're minimizing the runtime, the theta, of ai to k multiplied by ak to j. So that's just what we want to do. We just want to find, and we're choosing k. So we're minimizing this total, knowing that we can play with k and I and j are fixed. So yeah, I'll just say using k. So k is the variable here that we can play with. I and j are fixed. They're arguments. Turns out that that's actually, you know what, I want to use this board because I just want to continue below. Turns out that that's not a crazy starting point. And we can work with it. Can anybody propose a sort of next step? Maybe we might want to say something with that. Like maybe we might want to say, okay, well let's track that number. So we know we want some sort of matrix. So let's track the number in some sort of like minimum number of computations matrix. We're going to want one eventually. So let's throw in So we're going to say that this equals the minimum subject to the idea that I is less than k. I'll put it over here. So we'll just say the minimum of theta such that right? So that's our sort of top level structure. Can anyone think of a sort of an alteration we can do to jazz that up? To take us we just want to get one step closer. Right now we're really still talking about the global problem given at I and j, but we know eventually we kind of want to talk about subproblems. It's not clear how to incorporate this yet. Does anybody have any ideas on the next sort of step? Like, I mean, I sat down and thought about how to formulate this, so I don't expect that you might necessarily be able to come up with it on the spot, but maybe. The first thing we might want to do is, we're talking about placing one bracket. So we might want to consider, if we're going to optimize our one bracket, our k value, which has to do with this bracket, we might want to actually make a formulation that characterizes the choice of that bracket, which turns out might look something like this. What did I say? Yeah. So it turns out that it's going to be this plus the runtime. No, this is too far. This plus the runtime of, yeah. Plus also this runtime. So we're talking about the subproducts when I write the theta notation. I'm assuming that we're talking about the effort in terms of multiplication. So this is a kind of a key move here. This is the key moment. Do you guys kind of see what I'm talking about here, loosely? So the idea, we're talking about the global problem here, and then here we're talking about the idea, well, this is the cost of this bracket and multiplying these two subproducts, right? So if we want to think of this as like product, the sum of the products of one and the effort, the raw multiplication effort that was consumed by doing this first product and this product. Okay, we've done that already. It's in the past, right? And so really, this is we know that from over here, you know, if I successfully convince you that, you know, when we combine these subproducts, what to do is take the first index and the last two. Yeah. Right. Okay, yeah, so all we have to do is take these three, multiply them together, and we get the cost plus the recursive cost there. And this should get you really excited because we're pretty much one step away from a sort of recursive formulation. So really, if we want to set up n to be able to track our multiplication cost, then the true runtime isn't going to be a good indicator. So these are at best proportional. So let's just do that and make you guys angry in your notebooks. But what we can really set up the equality now. And I didn't want to blow through it too fast. It's one. You know what? We're missing a min here. So we have to do a min k here. We have to minimize subject to k. So we're still doing this minimization with k all the way across the board.
So, so does that minimization apply to the whole equation or just the first term?
Sorry, the min?
Yeah.
In this case, to be honest, if we're assuming that these are efficient, then it can. It's really just this part, right?
Okay.
Yeah. This part, we're assuming it's kind of done efficiently, but we kind of, and when we're doing this loose sort of thinking about the problem, we're going to work our way towards being more specific. So we're definitely assuming that these happen in the most efficient way possible, and we're assuming that they are the minimum. So maybe our theta, we could say our theta is the most or the lowest cost that we can get from doing those products. Yeah, and then at this point, it becomes kind of easy. Yeah, anyway. You know what? The minimization is the whole thing because these two depend on K. So, sorry, I was jumped the gun. Really, and how's the time am I doing here? Oh, great. That's perfect. And this, I think, is the total deal. A few box around it. Were you guys told to do that on tests and things when you did something good? Like, draw the box around the answer. No? So your markers would know. Anyway, that's kind of what we end up with. So what I really wanted to impart, because this is a class about deducing these sorts of things, and there's no rule to how to come up with these ideas, is I really wanted to go slow and work through, that eureka moment. When you start with this idea of, I just want to minimize the amount of computations. I don't know, you just write down some random equation, like, I just want to minimize this. This is what I want to minimize. And then if you look at it sometimes long enough, you can think, well, hold on. I don't actually want to minimize this directly. I want to minimize the thing I'm going to do to this. I want to minimize the computations plus the sub-computations involved with this. And then you realize, well, it's recursive. So I mean, if I have this minimum number here, then I can specify it in terms of this cost plus two others. Can anyone see how this is almost a recursive algorithm already? Like if you gave me a list of matrices, we could plug this in right now and figure out the cost, right? But it would be exponential because we'd be considering lots of overlapping subproducts by virtue of these. So it wouldn't be that efficient. Yeah. Does anyone have an idea of what we might do going forward to make this into a dynamic programming using memorization? What we might do?
Just keep track of those, and it's going to be a matrix, really, because it's 2 dimensions, and just reuse whatever we can in an iterative approach.
Yeah, so I just want to make an iterative application. What we have to make sure we do is we start with one, like these can only have one step at first. So we have to make sure we cover all the one step, like the one matrix products, populate those, and then the 2 matrix products, and the 3 matrix products going forward. We can't have null values, right? And that's it. So we're gonna walk through, like, we can't walk through that now. So yeah, I'll let you guys go, but that's it.